Hi guys, let's try to derive an expression for the talk on a magnetic dipole placed in a magnetic field. So here a magnetic dipole means nothing but just like a bar magnet. So this bar magnet we are considering as a magnetic dipole because it consists north and south pole. Now this bar magnet is kept in a uniform magnetic field. So let me draw a quick uniform magnetic field. So this is a uniform magnetic field which is representing in the direction, and take it as they are equally spaced so that uniform magnetic field is present on the screen. So let me take one more line. In this uniform magnetic field, suppose if I keep a bar magnet, so I will draw a small as bar magnet. So this in this uniform magnetic field, suppose if I keep a bar magnet, so this time I am trying to change the shape of the bar magnet, not like just exactly what we see as a rectangle. So just like to give a look like that of the electric dipole. Then that's good. Then we can do the comparative study. Suppose this is a bar magnet, and make sure that this is having uniform cross section. So if I do not make perfect exact shape, please do adjust. So this is a bar magnet. This is placed in the uniform magnetic field. So if this is north pole and this is south pole, and you remember very carefully, so these two poles are having pole strength. That pole strength we are representing with the little q suffix m. So this we define as pole strength. Pole strength of a bar magnet is equivalent to charge of an given electric charge. It's the quantity of the charge. Now, if Qm is the pole strength of the each pole, because it's a dipole, it's having two poles. So each pole having a pole strength of Q suffix m. And if I take this bar magnet length L as 2L. Now, if Qm be the pole strength of each pole, and we need to find first force on north pole of the dipole, of the magnetic dipole. To find the force, here we are having only two things. One is magnetic field direction, another one is what we called so far here, it is magnetic pole strength. Now here I am throwing a formula. That formula you just make a relation between force and magnetic field and magnetic pole strength. Suppose from the electric fields, if you remember this force and electric field relation, F equal to QE. The force F equal to QE, or you remember like this, electric field equal to force per charge. So this is also you can remember. So if you do the same analogy to magnetic field, to get the force F, so I need to here have, in the place of Q, we need to have magnetic pole strength, and in the place of E we need to have magnetic field B, or I can write a relation magnetic field B equal to force per magnetic pole strength, B equal to F times Q. Now I'll use this formula straight away at here because we don't have any kind of derivation, any kind of the basics of like that. Just we need to get a comparative study from the electric charges and electric fields and adhere to magnetic fields, because we are comparing the magnetic pole strength is equivalent to charge of a given electric charge. So here the force on north pole equal to pole strength times magnetic field B. And what is the direction? So if you can take the direction is, in this case it is along in this direction, means along B bar. Magnetic field is acting along B bar direction. Now further down another pole is there, force on south pole of the magnetic dipole, which equal to, so this time here same magnetic strength and magnetic field B. Now this time the direction will changes. Now the direction will be changes now along in this direction, because magnetic poles will be affected opposite forces. Now this side I can write that opposite to B bar. So here keep it in mind, here we don't have negative force, and if you see here clearly, two equal strength of forces acting oppositely, that causes a couple. Now that couple is a force, is causes to rotate magnetic dipole in the magnetic field, that causes torque. Now to find the torque we need to use torque formula, tau equal to, we know familiar about this torque tau equal to magnitude of the force on any pole, force times perpendicular distance. Now here we need to get magnitude of the force, here I already found that, and we need to get the perpendicular distance. Perpendicular distance means this is the one, if I draw a perpendicular across at here in the magnetic field, and this will becomes the perpendicular distance. Suppose if I make one right triangle at here, so if I can take this O at here, therefore OSN is form a right triangle with hypotenuse as 2L, and you can apply here, from that you can get it. So if this is OSN, it is S, it's O, it's N, it's a diagonal equal to 2L, and if I write sin theta equal to perpendicular upon hypotenuse. Now I need to get perpendicular, so perpendicular equal to hypotenuse times sin theta. So here hypotenuse value equal to 2L sin theta. So I got it the perpendicular value at there. So the perpendicular value here, we got it that as 2L sin theta. Now we can plug in that in the torque tau equal to force, the magnitude of the force on any one of the pole, Q times B times 2L sin theta. Now it's the cross product, don't read just like that a multiplication. So this you can write that as Qm cross 2L times B sine theta. And if you remember, this Qm cross 2L, we call that magnetic moment M. So this will turn as MB sine theta. Now in vector form, if I write, in vector form, tau bar equal to M bar cross B bar. So this is expression for torque on a magnetic dipole or a bar magnet which kept in an magnetic field. So that torque causes to move the bar magnet or to twist the bar magnet in the magnetic field, suspension magnetic field. So this is the expression for torque. And what about direction? Since magnetic field and magnetic moment and torque, the three are direction sensitive. And here you can see magnetic field direction is shown at here. Suppose if I take it at here. Now if I take so this directions you take for a moment. So this is north, east, west and south. If magnetic field is along east direction and magnetic moment, the magnetic moment always from south to north, it means it is showing along the northeast direction. Magnetic moment direction is south to north and magnetic field is east direction. Where is the torque direction? So that you can apply any right hand screw rule. Since all three are mutually perpendicular, for direction apply right hand screw rule. So it means the three are mutually perpendicular. If M bar cross B bar is always mutually perpendicular to the torque. So that's what we apply in the right hand screw rule. So then only if torque, now if you can rotate a cap, a bottle cap, you rotate that. So when you open you need to rotate in one direction and to close you need to rotate another direction. So depends upon your rotation, so the resultant direction will changes. So here also the resultant direction of torque depends upon M bar cross B bar. Suppose in the above case, in the above formula, tau equal to MB sine theta, if the bar magnet is exactly perpendicular to the magnetic field. If B bar is perpendicular, it means magnetic moment is perpendicular to the B bar. Now theta equal to 90 degree, and if B bar equal to 1 means unit. So I get it here, tau equal to as a condition, tau equal to M itself. So here I need to get one more definition for magnetic moment. So magnetic moment, how we define? We define magnetic moment as, in the earlier cases we defined that magnetic moment equal to 2L times Q. So that is the standard definition. We got it from magnetic moment. Magnetic moment M equal to the product of the length of the bar magnet times the strength, the pole strength, 2LQM. So this is the definition of magnetic moment. Or from here you define magnetic moment as a standard. So this definition says that the magnetic dipole moment may be defined as the torque acting on a magnetic dipole placed perpendicular to a uniform magnetic field of unit strength. So magnetic dipole moment is equal to torque of a bar magnet which placed perpendicular in unit magnetic field. Now this is how the magnetic moment definition has changed. Again I am repeating, magnetic dipole moment may be defined as, or it's equal to, the torque which is acting on a magnetic dipole. Use that word which is better instead of bar magnet. Torque on a magnetic dipole. Don't forget that magnetic dipole is nothing but bar magnet because they both are same. Torque on a magnetic dipole which is placed perpendicular, especially it is perpendicular because that angle should be 90 degree in a unit magnetic field. Here the B value equals to 1, then we can define as torque equal to magnetic moment. One more thing here, we got the units for magnetic moment M equal to as ampere meter square. So these units we got from the earlier chapters. So earlier chapter also we discussed about the magnetic moments. From the earlier chapter, magnetic moment, we have one more formula equal to the product of current times area. So this gives to us magnetic moment for a circular loop, any kind of the loop, we got it, the product of current times area. So here it is clearly evidence to us ampere meter square. But here if you think one more time, how this 2LQM will give us ampere meter square as units. 2L is length units, and what is the units for QM? Magnetic pole strength. So that units we do not know that, but we can derive the units at here, the SI unit. So it is very important at here, SI unit of magnetic moment. Since tau equal to mb sin theta, and I need to define magnetic moment M equal to tau upon b sin theta. So if you write units for torque formula, force times perpendicular distance. Force units are Newton and distance units are meter. And B means magnetic field, its units goes to Tesla. And sin theta, so it's having a unit, nothing we can write, that we can leave that. So this we can modify that Newton meter Tesla inverse. So which is also we can write Newton meter is nothing but joule. Newton meter is nothing but Joule Tesla inverse. So this Joule Tesla inverse is nothing but or ampere meter square, which exactly gives to ampere meter square. So again if you convert the joules and Teslas in terms of the known terms, energy and the magnetic field, so that will be end up at here magnetic moment equal to ampere meter square. So this is the units for magnetic moment, ampere meter square. And I would like to talk about when torque is maximum or when torque is minimum. When tau is maximum, so tau max is equal to tau max will be if angle between the magnetic field and magnetic dipole moment. If theta equal to the angle between m cross b, magnetic dipole moment and magnetic field, the angle between them theta equal to 90 degree, then sine 90 degree equal to 1, therefore tau equal to mb, which gives us maximum condition. When the tau will be minimum, tau will be minimum if theta equal to 0 degree, that is sine 0 degree value gives to 0, therefore tau value equal to 0. It means if a magnet lies perpendicular to the bar magnet, if a magnet lies perpendicular in an external magnetic field, then on that bar magnet more torque will act. If I draw a diagram, if this is magnetic field direction and if we keep a bar magnet perpendicular, if we keep bar magnet perpendicular bar magnet, now on this bar magnet more torque will be act, because magnetic moment is perpendicular to the magnetic field. This is magnetic field direction, and if you take north pole and this south pole, magnetic moment is always from north to south. Now the angle at here theta equal to 90 degree. Now in this case the bar magnet will align, it will be acted more force in that case. Or when it comes to down case, if you take this is magnetic field direction, and if a bar magnet is placed along in the same direction of the magnetic field, suppose this is the bar magnet and this is south pole and north pole, and magnetic moment direction is also same. Magnetic moment is always from south to north direction. Here theta equal to 0 degree, there is no torque, torque equal to 0. Here you can say that tau will be minimum.